maybe should I start?
Yeah.
Okay, let me start. Okay, so today I like to talk about Udwadia-Kalaba equation, which is kind of a method to derive the equations of motion for constrained system. So for example, let's consider like we have omnidirectional robot. For example, like Rapper Pi, like the old like Ross tutorial robot. So for this one robot, we can probably like easily derive the equations of motion or like try to refer to some references and derive the equations of motion. So we can model the single robot. Now, let's think like we bought multiple robots of them. And we would like to, okay, now we have multiple robots. We would like to carry some heavy things from place to place. So now you would like to, for example, like put some bars or like plates on top of it. So for example, let's think like you prepare bars connecting between each other with ball joints, for example. Then to design a controller for autonomous control, we would like to derive some system dynamics of this. But the problem is like, okay, we would like to move this robot in this direction or like apply force in this direction. Then when we apply force in this direction, it is going to affect the other two robots because it is connected with the bar. And also, like at the same time, because it is autonomous controller, so you also apply some force to this robot. Then it is also going to affect the total force that is contributing for moving this robot. So there are some interrelation between them. So it is not trivial to derive the system dynamics of this. But this Udwadia-Kalaba equation gives us a way to derive the equations motion in a closed form. So like we do not need to like solve the equations of motion or like with the, how to say, like equations. So I would like to use the towing vehicle as an example for deriving the equations of motion using Udwadia-Kalaba equation. So to do this, we first consider about unconstrained system. Yeah. So like from now, I'm going to consider about like tires vehicle. So we have surface vehicle and we have underwater vehicle. And these vehicles are connected with a rope. Let's assume that the rope is a rigid body for simplicity. So let's say the length of the rope is L. It is fixed length, but it can move freely. Okay. So to derive this equations of motion for this system, we first consider about unconstrained system, which means that like we consider about equations motion of the surface vehicle and underwater vehicle independently without considering any interactions between them. Probably you can derive the equations motion of each vehicle independently referring to some references. For example, like Fosson's book for surface vehicles. And say like we derive the equations motion of the surface vehicle as this. And for underwater vehicles, as this. Simple. And let's combine these equations motion by defining general coordinate as like q to be like qs and qb, and also like fu to be fs, fb, and m as block diagonal matrix as this. 0 is the zero matrix. Okay. Then we can combine these equations motion as m times q 2 dot equals to f u. Is okay? Yep. So next thing we would like to consider is geometrical constraints. So now we are going to consider about the constraint that we have between these vehicles. So the geometrical constraint that we have is the distance between these two vehicles are equal to L, or like the norm of these is equal to L squared. So the position of the surface vehicle and the position of the underwater vehicles, the distance between them is this. PS is the position of the surface vehicle. So like it's part of this QS. Okay. Then let's bring this L square to the left hand side, and let's denote the function as like PS minus PB, the norm of it minus L square. And let's take the time derivative of this function. Okay. So phi dot equals to 2 PS minus PB transpose and PS minus PB. And let's take one more time order derivative. Then it will be like, oh, I forgot. I. It will be like this, right? So now we have this function have q dot and q, and here we have q2 dot. By arranging this equation, then we can fit. Okay, let's derive. So, so by putting this part in the right hand side and putting this part in this A matrix and this to here, then we can rearrange this equation in this formula. So anything like geometrical constraints that can be written as in this form or in this form can be summarized in this equation. For this pattern, as we did by taking second time order derivative, we can insert in here. For this form, by taking first time order derivative, we will have Q2 dot, so we can derive in this form. Okay.
So
Yep.
just to follow up, so in geometrical constraint, so those two, like the PS and the PH, are just the points, correct?
Yes, just the
And
position.
Position points, okay.
So
And
like
connected by the L2. L,
yes,
sorry.
yes, 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 yes.
Connected by L, okay.
So let's say like we connect in the like central position or something.
Okay.
Maybe we can write down if the Q is like including the position and orientation, yo, pitch, roll pitch yo, then it can be
Okay.
written as this.
Okay. And then the final thing that the zero.
Yes.
Yeah, this one. So what we are trying to say that this complete equation, when does it becomes to the zero?
So like if this, so like geometrical constraint saying that this phi q should be equal to 0.
Yes.
To achieve that, we need to have this phi dot also equal to 0.
Okay, if that is zero, okay.
Yeah, because it's 0, it should not move from 0.
Okay.
And then again.
Okay, I got the follow-up. Okay, that's great. Thank you.
That's kind of like intuitive understanding of the time derivatives of this. Okay. Then according to the UKE, the equation's motion equals to Fu, which is the force that is derived with this deriving equation's motion with unconstrained system, without considering any interaction between them, plus constrained force, where Fc can be derived by the following formula. This is very long, but it's useful. Wow, it's so this is like m half, m how to say m half of power. Power of half. For general matrix, we sometimes cannot define unique one, but if M is positive definite, which is usual case for physical system, then we can uniquely determine the half power of this. So the definition is like the matrix that satisfies this. Okay.
I have a question again. So from the unconstrained system, the equation mg double dot equals to fu, with the last one, yeah. Then when you come here, we add like plus fc. Okay, so the fc is a friction here?
So it's the tension force between these two
tension force, okay.
in this case. If you have multiple constraints, multiple geometrical constraints, for example, like normal force plus friction, normal force plus the tension force, then we cannot distinguish easily. If the direction is independent, then we can derive like each of the
So here
force.
the direction is independent in this case. the example what we have taken, the
Here?
towboat and the
So like, because this is like Q2 dot, Q is the combination of QS, QB. So for example, if we assume, okay, for simplicity, like we consider about point of mass system, like point of mass, then we have the position of surface vehicles in X direction, Y direction, Z direction, and position of underwater vehicle in X direction, Y, Z equals so M plus FC. So this FC shows also have like 6 components.
okay.
So first part is the tension force that is acting on the surface vehicle. And the later 3 is going to be the tension force acting on the underwater vehicle.
And this equation where the FC, from where we got it? Like each.
So this is kind of like, so like Udwadia Kalaba equation is saying like the constraint force can be derived in this formula.
Okay.
To prove it, we need to prove this, it is using the assumption that the constraint, geometric constraint, is smooth constraint. That means the virtual work is equal to 0. So for example, this force, so this is a limitation of Udwadia-Kalaba equation. So we cannot derive, for example, kinematic friction force, because the kinematic friction force, the virtual work is not equal to 0. It has like energy is going to be dissipated. So we cannot derive such kind of force from here. So the limitation is that, and in those cases, like if you want to model or if you want to include those terms in the model, Udwadia-Kalaba equation, Udwadia and Kalaba is suggesting that you can try to model the system as like adding one more term and try to model the force independently. But at least like with the Udwadia-Kalaba equation, we can derive sometimes good enough model of the system. And one good point, one advantage of using Udwadia-Kalaba equation compared to, for example, like Lagrangian method, is that we can derive the constraint force explicitly, like analytical form. So we don't need to again like try to solve the equations of motion to derive this, or like try to numerically solve the Lagrangian. So maybe I will also derive the equations motion of the first example. Okay.
Then I have like follow-up question. So I thought that this is a kind of recipe. Like I do the step 1 where I design the unconstrained system. Okay, I have that way of representing the complete system, the MQF equals to FU, the down equation. Then I go to the geometrical constraint. Okay, the second step. And the third step, I come to this thing, okay? But still, I didn't get the connection between the 2 and the 3. Like, are we using the 2 information somewhere in the 3?
Yes. So the matrix A and vector B is used in here.
Okay. Now I see. Okay, that A and B. Okay.
Maybe I can explain more with the next example.
Okay.
Next example is much simpler. Yeah.
Okay.
Okay. Let's.
So I know.
try to derive the equations motion and try to review this stuff and try to figure out the relation between this and this.
Yeah, now I got the FC. Like, okay, the M is coming from the above one. A
Yep.
and B are coming from there. FU, we already know it's coming from the unconstrained
equation.
system. Okay.
Yep.
Now everything makes sense. Okay.
Yep.
Okay. Thank you.
Okay, so for the one robot, let's think about this is the point of mass for more simplicity. So M Q1 2 dot equals to U1, and Q1 is the position of the robot. And for other vehicles, let's assume that the amount of mass is the same. So we can independently derive the equation of motion. Then by combining these, or by combining these, it will be like this. So the M is diagonal matrix. Q is Q1, Q2, Q3. And FU is U1, U2, U3.
So these are the forces on each axis.
Yes.
Okay.
Or yeah. Or if we consider about the two-dimensional space, it's the
Only
two-dimensional
2D. Okay. But here we are considering 3.
So like this is for the first robot.
Okay.
This is
For robot.
yeah.
Okay, for each robot. Okay, sorry. I thought like when you start like the robot with point mass.
Sorry.
Yeah.
Like this.
But we are working in 2D, right?
Yes, in 2D. The plane. So each Q1, Q2, Q3 have 2 components.
Yeah.
Then the geometrical constraints. Then the geometrical constraint is simply like the distance between Q1 and Q2. It's L, here L, and here L. If we say like this distance is L, 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 and because of the geometry, it is always be the perfect triangle?
Equilateral. Equilateral triangle.
Equilateral triangle. Yeah, yeah, that one. Yeah.
All 3 sides, sorry.
So let's take this as an example. So Q2, Q3 equals to L squared. And Q3 and Q1, the distance is L. Okay, for this one, exactly the same. We can derive the second time order derivative as this. The square of the difference velocity plus this one. Then,
So no need for the first derivative. It's fine.
yeah, by
it's
just
fine.
second time order.
Yeah.
by considering this, then it will be like right? So we can, because by distributing, we can derive here, and this part will be here. Oh, I need to put minus. Right?
Yeah.
Yep. Let's just do one more. 2, 3 equals to 2 q2 minus q3 dot mine plus 2 q2 minus q3 transpose q2 2 dot minus q3 2 dot. So by taking this equals to 0, then it will be, there is no 1, and here, and here. So by doing the same thing for Q31, the geometrical constraints, the second time order derivative of them, can be summarized as Q3 minus Q1 here. It can be summarized in this form. So let's denote here as A, Q. We don't have Q dot NT, but for consistency, let's denote it as this. And this part, this vector, to be B. Then according to UKE, the equations of motion and the constraint force can be derived with this form. So as we discussed, for this matrix M can be derived from this one. We know the mass of each of the components, so we know the matrix. And so M is okay. I think I should do it. So we know this, we know this, we know this. And FU, which can be like control input, for example. And so we know we can design the control input. Yeah. And for B and A, in this case, if we know the positions of the robot, then we can get the matrix A. We can evaluate it. And for B, if we have velocity, we can evaluate it. So if we have the position and velocity data, we know we can evaluate A and B. So we can derive what kind of constraint force it will be, depending on, for example, like control input in this formula. And also we can know like what kind of acceleration it will be for this system, because we know M and FU again. And yeah, because of this, we know S. We can kind of like evaluate or estimate FC depending on FU. So we know the acceleration from here in closed form. That's a strength of UKE for deriving equations of motion, I think. Yes, that's all I wanted to share for today. Thank you very much for listening. Do you have any questions? I think we discussed.
Yeah, it's nice to see. It's like the coupling shows in the FC, right? How they are coupled and by how much they are coupled. Like they are acting as a collective mass, right?
Yes, yes. So like if you want to some model, for example, like ropes, then we can also consider about like these are connected to each other. And for each part, like by assuming it's a rigid body, for example, then we can probably derive the equations of motion using this Udwadia Kalaba equation in closed form, which can be used for like deriving the control input, probably.
And A doesn't have to be positive definite, right?
For M,
A.
A? Yeah, A doesn't have to be. Yeah.
Doesn't have to be.
The only assumption in geometrical constraints is that geometrical constraints are smooth constraints. There is no virtual work due to this constraint. So yeah, one strength part that is suggested according to papers compared to Keynes equation, this geometrical constraint can also like treat holonomic constraints and non-holonomic constraints. So like it is not just with Q but with Q dot. So we can treat them as like kind of like same things for this. Yep.
So do you have like any Python or simulation code that you're using this so we can play?
Not the thing that you can play because it's the simulation itself. It's like yeah, like I cannot distribute to anyone because it's a confidential thing.
It's an active research.
Yeah, but the paper that I'm going to present in IFAC is related using this one. So yeah, I can give you a simulation, but you can take a look at it. But it's basically the same. Like the main part is.
I really like the recipe. Okay, so I was just thinking like more to understand.
Yeah. So like the point in like to use this one in simulation, it's just like writing this equation. That's it. So and try to derive this A and B. This is the tricky part. So like you need to usually like differentiate twice. And yeah, deriving. So for this example, it's very simple. But
So
the
that's
other
why
example.
you use the word smooth or continuous because we have to have an like differentiable.
Yes.
Now it makes sense.
And I mean like smooth constraint. So like it should be smooth function, but the reason why we need smooth constraint is that here we have Muro-Penrose inverse. So it is like
Which inverse?
Muro-Penrose inverse.
Can you write it?
Muro
Ah,
Penrose.
okay, Murray. Okay.
Yeah. I think
Murray
Axel can
Penrose.
explain more about this.
It's like Murray Penrose, the bridge.
Inverse. So
Inverse I got, but there's like paper which maybe different. Okay, continue.
it's kind of like trying to derive the generalized inverse.
Generalized
Inverse of the matrix. So you have like matrix A, and if it is not square matrix, we cannot derive the
inverse.
inverse. And also like, if the determinant equals to 0, we cannot derive that, right? But I forgot the exact definition. Like there, I think like there were like 5 properties that it needs to satisfy in order to say, okay, this is Muro-Penrose inverse. Basically, what we would like to find for even for generalized matrix is that like if some matrix times A matrix equals to identity matrix, and A matrix times the matrix equals to also like identity matrix, we would like to say, okay, these matrices are inverse because it is going to be identity matrix. And for general matrix, there are many matrices that satisfies this.
Okay.
If it is only one, then we can define it as it is, okay, this is inverse. But for general, it's not. So like we have other property that must be satisfied to say, okay, this is Muro-Penrose inverse. But Muro-Penrose inverse gives us Muro-Penrose inverse gives us the minimum difference between AX and B. So like the, okay, so minimum of this, the X is going to be denoted as this. So Muro-Penrose inverse satisfies this. It's like, I forgot the definition, 8. Do you remember?
What?
No. Yeah. So actually, because we are using Muro-Penrose inverse here, so if there are some virtual work is not equal to 0, then there will be some terms here. So it would not like, because virtual work is equal to 0, we can take the minimum value of the difference between this. And it will be like, the result will be like this. But if there is virtual work, then those terms cannot be minimized, like it cannot be equal to 0. So we will have some terms and we need to model them. So yeah. That's what I mentioned earlier in here. So like we can add one more term to model, for example, kinematic friction force.
Okay, that's cool. Thank you.
Thank you.
For sharing.
Thank
Thank
you very much for coming.